Hello, this is Eric Falk again, and we are going to do the AEC example number 10 of the structural section. And the purpose of this example is to find the moment of inertia, which is also known as I, about the centroidal axis, which is also called the neutral axis. But it's always going to have the same excuse me, the same moment of inertia no matter where you take it of. If you don't know the centroidal axis or the neutral axis, same thing, you need to figure it out to find the moment of inertia. So what we're going to do is we can go ahead and I'm just going to justify the centroidal axis. We did this on the last video. But the centroidal axis is the sum of area times distance over the sum of the areas. And we're going to go ahead and just say, hey, obviously this is a rectangle. It's pretty darn easy to figure this out. So we're just going to do it real quick to justify, hey, is it really halfway? And you can prove yourself that, hey, this actually works. So we're going to do the sum. Well, let's just say, let's break it into two boxes just for fun's sake. Let's call it A1 and A2, and let's do it from the base down here. So A1 is what? 5.625 inches times 3.5. That was your area. Now you want to do times distance, and your distance is A1 is 5.625 plus half of this 5.625. So 5.625 times, let's say 1.5, is 8.4375. And that is that. And then, this is kind of a mess, so I'm running out of space because I didn't plan it well enough. But let's go ahead and do this. You're going to have the same for area because it's the same shape. 5.65, 3.5. And then you want to do what's half of 5.625, because the distance from where you're taking it, the base, to halfway is half of 5.625, and that is 2.8125. Okay, that is your area times distance, your sum of your area times distance. This is A1, this is A2. Then you want to do sum of areas, which is 5.625 inches, 3.5 inches, and then this is the same thing. You could multiply by 2, but just in case they weren't exactly the same. Alright, let's go ahead and calculate this out and justify that the centroidal axis is in the middle, and this equation does work. And when I punch this into the calculator, I get 5.625, and that was from the bottom right here. 5.625 is where it says our neutral axis is. So obviously this has already been calculated for us, and everybody knows, well, the centroidal axis is halfway because you have equal area on the top and the bottom. So that's obvious, but we just showed the equation to get it, and that's just to get you used to doing that. Now we're going to move on to the task at hand, and we want to know I. I, as I said last time, of a shape like this is BH cubed over 12 plus AD squared. And when you take a look, we'll start with A1 and then we'll go A2. And another thing is, you could look at it as just one big piece right here. You can look at one big piece, and it's about the neutral axis, so the D would be 0. Let's do this first, actually. Let's do it twice. Okay, so when we look at this, it's BH cubed over 12 plus AD squared. Well, we know D, if we're looking at this as one big, let's call it A3. So we're not doing A1 and A2 anymore. We're doing A3 is the entire section here. I'm going to go backwards though. A3 is the entire section. So we know that D from the centroidal axis, that distance is 0 because it is the centroidal axis. Centroidal axis is the same as centroidal axis of the entire section. So this will go to 0. And then you just have BH cubed over 12. So let's go down here. Base is 3.5. H, that's 11.25 inches cubed over 12. Keep on. And that answer is 415.3 inches to the fourth. And you can go ahead and check the dimensions. It's typically going to do inches to the fourth. Seldom will you see this in foot to the fourth because that's a pretty darn big section. But the inches to the fourth will always give you, this is a pretty small section, but you'll get up to pretty decently high numbers if you have a big, larger section in the thousands and the tens of thousands typically. But you have inches times inches cubes is inches to the fourth. So you're good, and we're going to go ahead and check that with the solution in the practice exam here, and it's 415.3. And I usually do not carry it out to this. I'll just do 415 and call it good. Usually you're not going to have that big of an issue with an inch to the fourth. You're not going to have an issue with that. All right, now I want to go ahead and do this equation as well if you were doing it for A1 and A2. Initially we just did it for A3, which we called it was the entire section. So now let's do it. I'm going to change colors real quick. Let's do it for A1 and then A2. Let's use a gold color. So that's A2 and that's A1. And what the purpose for me doing this is the easiest way is to do it what we just did. BH cubed over 3, BH cubed over 12, sorry, plus AD squared. But the D obviously goes to 0 if you're doing the entire section. But let's practice doing it as if we had to do it with 2 sections for some crazy reason. So it's going to be a longer calculation, but it's still not too bad. We have the time. So let's go ahead and write the equation first. And that's the best way when you're doing calcs to do, is just write out every single equation. It's easy to follow. People who are coming after you can say, where in the heck did he get that? And it gets to be very, very confusing if you don't write out your equation, which it's okay if somebody knows what they're doing, but even the most experienced engineer can look at somebody's calcs and not know exactly what they're doing. So it's best to follow, put your equations, and then you can even, let's say this comes from code, you can say, well, for instance, this comes from IBC 3.6-2. Obviously this is completely made up because I have no idea. Well, first, IBC doesn't have this type of stuff in it. It more has loading things. Anyways, to continue on, we're going to do A1, then we'll do A2. So A1 is the base is 3.5 inches. The height is 5.625 inches. And that's cubed over 12. And we should get the same answer here that we got right here. But we're just going to justify it in practice as we're doing it. So A is 3.5 inches times 5.625 inches. That's your area. And then you want to do distance. Okay, well, distance from your neutral axis to the centroid of that is, let's just do it this way, 5.625 inches over 2, because we know it's halfway, and we're just going to square that. Then we pretty much do the exact same thing again, because it's the same section you're going to have. And this is A2. Let's just put it in gold, so maybe color coding will make it a little bit less confusing what we're doing. Now we're doing A2. A2, the base is 3.5. The height is 5.625 cubed over 12. Remember, this only works for cubic sections, not cubic sections, but rectangles or squares or whatnot, rectangles or squares. So that's BH cubed over 12 plus AD A is 3.5, 5.625. That is A, length times width. And then you wanted to take D, which is, well, 5.625 divided by 2. And you want to square that. And then when we go ahead and get the calculator out, and run this, we get, it should be 415.3, but let's check it. And when I calculate it out, it becomes 415.3 inches to the fourth. Exact same answer. So you're good to go. We have about 4 minutes left max. So I'm going to go ahead and clear this. Clear this up real quick. And what I want to show you is a little bit of intuition regarding the moment of inertia. And I've touched on this in other videos, and I'll probably make some general instruction videos in time, but here we are, so here we go. You have your neutral axis at a shape, and this is the reason you'll see most I-beams are I-beams. It's more efficient than, say, just a bar. Why don't you just have a big old bar right here? It's because this I-beam, it has more area away from the neutral axis. So look at all this area. This is a huge area away from the neutral axis, and that's a good thing. That will help. And you can kind of take a look at it. What it does is, in moment, it makes a force couple. When it tries to rotate, it makes a force couple, and the further you have it away, the more it resists, the more efficiently it resists that force couple, and that's why it is good to have the higher I. And if you take a look at your steel book or whatnot, you can take a look at different sections, and typically the higher you'll see, like W30s and these are wide flange sections, where I-beams, some people call them, W24, or let's just say W40, something huge. I'm making this up, but 57. There's not a W57. Usually what these mean are, this is how high the beam is in inches, and it's not perfect, but it's based on the I. All these, I'm sorry, that's going to be confusing. The T, usually it's this distance from this distance, is all the same on all these different beams. So anyways, generally you can say, oh, a W30 beam is going to be 30 inches tall, and a W57 is going to be 57 inches tall, or a W24 is going to be 24 inches tall, in general, of course. But this W57 is going to be a more efficient beam in general. You can have the same weight W57 beam, and you can have the same as a W30 beam, but that W50 or the W30, let's do 30 and 24 beams. The W30 beam is going to be more efficient than the same beam weighing. So let's say this is W30, and this is W. That's horrible. Anyways, W24. They may weigh the exact same, because this one, let's say, has a little bit more weight on a little bit more area on these flanges, a little bit more area on the web, and that's okay. But since this has more of the flange is further away from that neutral axis, it's going to be more efficient. Generally, you'll see that. And that's just some intuition. You'll see like a C-beam or an angle. Angles aren't the best in bending. So you'll see everything that's based on bending is going to be this wide flange. You also will see like the HP sections, which are typically more square. They kind of look like this, and let's say a typical, this will be 12 inches, and this will be 12 inches. Those you won't use for moment type resistance, because it's not set up for that. Stuff with a long web is better because it gets you further away from that neutral axis. This is used for columns and whatnot.